In this video, we will take a look at using elementary row operations and solving systems of equations that have special solutions, the infinite number of solutions and the no solutions. Now, in the last video, we used the three elementary row operations to get our augmented matrix in the form something like 1, 0, 0, 1, and then whatever the x coordinate is of the answer. That is really bad penmanship. This is not being very cooperative. And the y coordinate of whatever the answer is. Okay. And in this video with special solutions, we're going to find that no matter what we do with elementary row operations, we're never going to get the left side of this augmented matrix to have ones on the main diagonal and zeros elsewhere. So let's take a look at part C, which I believe this one was an infinite number of solutions when we solved it last. I believe it was in part 2's video. So let's start by writing the augmented matrix. We have 1, negative 2 in the first column. We have negative 1, 2 in the second. And we have negative 3, 6. All right, well, once again, our goal is to start by getting this first value equal to 1, which it already is, so that's really nice. So let's look below that. We want to get this negative 2 equal to 0. So if we take the opposite of negative 2, that's positive 2. So if we multiply row number 1 by positive 2, so 2 times row number 1, and then we add it to row number 2, we can make that our new row number 2. So let's see what we get. First row is going to stay the same, only row number 2 is the one that changes. So 1, negative 1, negative 3. 2 times 1 is 2. 2 plus negative 2 is 0. 2 times negative 1 is negative 2. Negative 2 plus 2 is 0. And 2 times negative 3 is negative 6. Negative 6 plus 6 is 0. All right, so notice in this bottom row, this row number 2, we have a whole row of zeros. And when that happens, especially to the left of this vertical line, no matter what elementary row operations we try to use, we are never going to get the left side of this matrix to be the identity matrix in the form 1, 0, 0, 1. It's just never going to happen. In fact, if we were to look at these values as the coefficients of the variables, this last row is saying 0 times x plus 0 times y equals 0. Well, 0 times anything is 0. And 0 plus 0 gives us 0, so we're left with a true statement. 0 does equal 0. That's a true statement. And so in this case, since we arrive at a true statement, we have an infinite number of solutions. In other words, if we were to graph these, if we were to graph the rows, they'd be the same line. If we were to graph them just like we did in example 2C, where we looked at the transformation of the coordinate plane, that's where it squishes down to becoming just a line. It's not a grid anymore, it's just a line. And the point, oops, didn't mean to do that. The point negative 3, 6 is on that line. So from an elementary row operation point of view, we have an infinite number of solutions. Now, it turns out there actually is a way to determine, looking at our system, if we'll have an infinite number of solutions, and that's if one row is some combination of row operations of another. So, for instance, the second row that we have here, all three values, is just taking the first row and multiplying it by negative 2. So if you took negative 2 times the first row, you're going to get negative 2, 2, and 6, which is what your second row is. So that's going to lead to an infinite number of solutions in that case. All right, part D. Here is one that in previous video, I think in part 2, we said that this one had no solution. So we transformed the coordinate plane and it's a line, but this time the point 610 was not on that line. So let's see this using elementary row operations. Elementary row operations also are very good for our like three-dimensional and higher dimensional systems of equations because it's very hard to visualize those using even a computer. And whether you're graphing the rows or graphing the columns, it can be pretty daunting. So this is a nice generalized way to solve systems no matter what. All right, but anyway, we have 3, -4, and 6. Here we have 6, -8, and 10. And if you're looking at this, we have 3 times 2 is 6, -4 times 2 is -8, but 6 times 2 is not 10. So this one's going to be, it doesn't make all 3 numbers when you multiply by 2. You don't get all 3 values in the second row, which means this one is going to be a no solution. But in any event, we can start, if we get this first value here equal to 1, we can do that by dividing the first row by 3, which is the same as multiplying by 1/3. So if we multiply our first row by 1/3, or take row 1 and divide it by 3, we'll make that our new row number 1. All right, so 1/3 of 3, or 3 divided by 3 is 1. We're going to get -4/3, which sounds scary, but we already know that we're not going to have much more work to do beyond this step here. We might have one more step. And then 1/3 of 6 is 2. All right, so now we want to get this value equal to 0, and the best way to do that is going to be to take the opposite of that value, which is -6. So we take this first row times -6, so -6 times the first row. We can add it to the second row and store that as our new second row. And we're going to see that that's going to be the last thing we're going to do in this problem. So once again, row number 2 is the one that's going to change, so we can keep row number 1 as it is. -6 times 1 is -6. -6 plus 6 is 0. So we got that first column set. -6 times -4/3 is +24/3, which is +8. +8 plus -8 is 0. So there's some zeros there. And then -6 times 2 is -12. -12 plus 10 is -2. And again, we have to the left of this line, we have a row of zeros, which means no matter what elementary row operations we try to do, we're never going to get this left side to be the form 1, 0, 0, 1, to be this identity matrix form. So let's look at this last row. We have 0, 0, and -2. So if we put the x and y back, this would be 0 times x plus 0 times y equals -2. And we know that 0x plus 0y is 0, and 0, unfortunately, is not equal to -2. We get a false statement, which means we have no solution. Just like in example 2, part D, but this time using elementary row operations. All right, that about does it for this video. Thanks for watching. I'll see you next time.